So, we have learned that whenever we make a measurement, we never make one measurement. In order to get a value of a parameter or a variable, we always make a number of measurements, and from there we try to obtain what is a reasonable value that we can state. The idea is that anybody anywhere in the world, if that experiment is repeated, he or she should get the same result. And for that purpose, we have to state the result that I have got as well as the error bar. And the basic concept was that we have to make a number of measurements and there is a minimum bound to the number, which is around 25 for a measurement of a value. While if it is a measurement of a proportion, that number is far larger that we have seen. The second point is that the idea was that whenever we are making a measurement, there is a population out there and we are taking samples. Even when we are measuring something like the mass of an electron, we are making say 25 measurements, 25 readings we are taking, but we know that we could have taken an ideally infinite number of measurements, and if we had done so, then the average that we get is a reliable estimate of the mass of an electron, but we cannot take that. So, there is a theoretically ideal infinite number of measurements, that is a population, and from there we are taking a sample and we have got a value. If we had taken a different sample, that means we had made the measurement with another 25 readings, we would have got a different value. So, a third time we have got another different value. So, there would be a distribution of the means that we get, and the central limit theorem ensured that the distribution of the means would be a normal distribution. Once you had that, then the idea was that the mean of the normal distribution of the means, the mid value would be the population mean, and we have got a particular value, then we can talk in terms of the confidence level with which we can state that the population mean will lie within a certain range of the mean that you have got, and that range is the range is given as the error bar. The standard error of the mean is stated as the error bar, and in different areas there are different confidence levels that are demanded, and based on that we define different confidence levels, and therefore, the error bar is defined with the appropriate confidence level, which is appropriate for that particular field. In some fields it is basically one standard error, in some fields it is say 95% confidence, which is 1.96 standard error, and so on and so forth. So, this is something that we have learned, and we have learned that sometimes in a data set that you have got, there can be outliers. The outliers happen because of various reasons, that they may happen due to instrumental error, they may happen due to a error in measurement, they may happen due to some physical phenomenon, that is also possible. And so, whenever we have got a value, measured value, which is apparently a bit incongruous out of a range, then we have to define the range that we will define as reasonable, and that is done by the box and whisker plot, which is done not on the basis of the means, but on the basis of the medians. The median and the max, their median, the median and the mean, their median, and then that defines the interquartile range, and the minimum value minus the interquartile range, the minimum value means of the box minus interquartile range, that defines, let me just clarify it once again, because there is sometimes a confusion about it. So, you have the box and you have the whisker, sorry. You have the whisker. So, the whiskers are designated like this. Here is suppose the median of the whole data set, and then the median of the, this is the max and this is the minimum value of the data set. The median of this is the end here, the median between median, this median and the mean is the end here. So, this defines the box and this range is the interquartile range, and your this point plus 1.5 interquartile range is the acceptable range of the data, and this point minus 1.5 IQR is again defines another acceptable range of the data. And suppose this point actually comes here. Okay, so, this value comes here. Therefore, this mean value or whatever is the data here, that is an outlier, and in that case we specify that as an outlier like this, and then the minimum value becomes the lowest value of the data set that is above this value. Okay. So, we will have to, maybe it is here. So, then that becomes the mean. Okay. This is how the whole thing is done. Now, notice after this is done, then this data point goes out and a few data points remain, and the things that we have talked about regarding the calculation of the mean, the standard deviation, all these, and I mean standard error of the mean, the confidence interval, all these calculations can be done with this, the remaining data set, leaving out this outlier. So, this is the outlier. But the outlier has to be presented in a paper as an obtained data value. You cannot by yourself eliminate that, because there may be information contained in the outlier. So, if you have done all the calculations with the data set and then later you identify an outlier, you might have to do the entire calculation again excluding the outlier. That will be more reasonable thing to do, but always point out that there was an outlier, that is the point. Okay. Fine. So, with this we have learned how to represent a data. This is the box and whisker plot, and normally in most presentations we present it as a data point with an error bar designated like this. Okay. Now, there are various situations in which you want to measure something, but you have access to something else which you can measure. Sometimes you can measure something and what you actually want to measure is a function of what you have actually measured. So, a situation like you want to measure some z which is a function of x, and it is the x that you have measured. There are certain situations where you have measured two values x and y, and the one that you want to actually measure may be something like z is equal to x plus y or x minus y or x times y. Now, the question then is that I have measured x as a value. So, I have measured x as a value and I have measured the standard error. How does it propagate as a value of z and a standard error of z? In this case, I have measured a value of x, that means a value as well as the error bar. Similarly, I have measured a value of y with an error bar. How do these propagate to decide a value of the z and the error bar on z? That is a question that we will deal with today. So, let us take the first issue first. Let us take the condition, let us take the situation where I have z which I want to measure is x plus y and x is being measured, y has been measured. I will need to define the symbols. What I will do is x bar is the measured mean value of x. Similarly, y bar is measured mean value of y. Now, the deviations from x, the bars, let us denote that as delta x and delta y. So, these are the errors. And y. So, basically what you have done is I have measured x with an error bar. So, x is specified as x bar plus minus delta x. Similarly, y is specified as y bar plus minus delta y, and then we are trying to find out how should we state z. Now, the mean value of z is easy to calculate, easy to understand. Mean value of z will be z bar will be equal to x bar plus y bar. There is no difficulty in understanding that. But how do the errors propagate? That is the issue. Errors means our delta x and delta y, how do they propagate to produce an error bar in z, delta z. Now, it is easy to see that if the errors are random errors, not systematic errors, these are random errors, then the errors in x and y are independently random errors. They are independently random. So, delta x can be positive or negative, delta y can be positive or negative, and they randomly occur. There is no correlation between them, and as a result of which in some cases the delta x, when you add x and y, sometimes delta x and delta y might add, sometimes delta x and delta y might subtract from each other. So, sometimes there will be larger error, sometimes there will be smaller error. Then what is the mean? It is something like this. Let us do it. Let us do that graphically. Suppose your x is this much, and suppose your y is say this much. So, if the z is this is just addition of them, then it would be like this. Okay. So, this is where they are adding up, okay? X and y are adding up to produce z. The other possibility is your x is here, and I'll better put with arrows, arrow. Here I have x, and from here I will draw the y, so that it will be easier for you to see. I will draw it this way. Y is this. So that your z, this z is only, sorry, z is only this much. So, in one case they were adding up. So, it was say delta x, this was delta y, and this was delta z. So, the errors added up because at the same time when x was in a positive direction, y was also in a positive direction. So, they added up. In this case delta x was in positive direction, delta y was in negative direction, and the delta z was naturally a subtraction of them. So, all possibilities exist. Sometimes they will add up, sometimes they will subtract, and intermediate possibilities also exist. Now, in statistics it has been shown, statistics has shown that on an average the delta z can be calculated as x being drawn, delta x being drawn like this, and the delta y being drawn in quadrature. That will be the average. That will be the average. So, this is our delta x, this is our delta y. So, this is delta z. So, since all the possibilities exist, they can add up, they can subtract, and all intermediate values exist. So, this can be this way, this can be this way, and the middle will be this when it is at the quadrature. Then it is easy to express your delta z. Delta z will then be expressed as delta x square plus delta y square root. So, this is how we express the error, standard error in the ultimate quantity z, and we will express z as z bar plus delta z plus minus delta z. This is how we will express. Okay. What if we want to calculate z as given as x minus y? In that case, the average value, the mean value of z is easy to calculate, that will be x bar minus y bar, no problem. But what about the delta z? Now, delta z in case it is they are subtracted, then also there all these possibilities exist. The errors can add up, errors can subtract, and all intermediate possibilities exist. So, delta y can be this way, delta y can be that way, and exactly the same situation will pertain. And therefore, the delta z will still be given as square root of delta x square plus delta y square. Now, notice one important thing here. As a result of the subtraction, the average, the mean value of z can be small, but the error remains the same. And therefore, whenever there is a subtraction, whenever we want to measure something that is a subtraction of two measured values x and y, then there is a possibility that the error might swamp the result itself. The error might be big, because that is not reducing because of the subtraction, but what is reducing is the mean value. So, the percentage error might be very large. So, in actual measurement, we try to avoid situations like this. We try to avoid situations where we have to subtract two quantities. This is an important lesson in planning an experiment. Whenever we are planning an experiment, we always try to avoid a situation where we have to subtract two values. When we cannot, we at least make sure that the two values are widely different, so that this value will not be too small. Okay. Fine. Let me clear this and let us continue. The next question is, what if z is equal to x times y? Then how would the errors propagate into an error in z? We have already learned that if you have two quantities that add with each other, how the errors propagate. We have learned that. Here it is not in that form, it is not in a addition form, it is in a multiplication form. But with a easy algebraic procedure, we can get it into a summation form simply by taking a logarithm. Ln z is equal to ln x plus ln y. Okay, easy. And now this is in a summation form, and if it is a summation form, then the error in ln x and the error in ln y, they would propagate in the way we have done already. That is the easy thing. So, we can easily see that by the same logic, the delta error in the ln z will be square root of the delta error in the ln x square plus the delta ln y square. It might be better to put a bracket to make things clearer. Okay. So, this is clear, but how do we know? We know we have measured x. How do you know what is the error in the ln x? That question we have to deal with now. Now, that is not difficult to deal with, because we know that d dx of ln x is equal to 1 by x, right. Now, this means if we now replace the d dx by the incremental quantities, small change kind of quantities, then the delta of ln x becomes 1 by x times this delta x, right. So, this is easy. Then we can substitute it here, and we can express the delta ln z will be delta z by z. So, delta z by z, that will be equal to, I substitute here delta ln x will be it will be delta x by x square plus delta y by y square, right. Easy to see. Now, if this is true, we can interpret these, each of these are actually the percentage errors. This is the error as a fraction of the value. So, these are actually the fractional errors, or if you multiply that by 100, these are the percentage errors. So, you see the way, if I measure x and y and I want to measure the error in z, which is x plus y, the way we did it, if we want to measure the error in x times y, we would do exactly the same thing. Only thing is that in this case, instead of the error itself, we will take the percentage error. So, in this case, percentage error replaces same formula with percentage error replacing the actual errors. Percentage errors represent actual errors. So, this is how we do it for products, where we have to take a multiplication. So, the same formula, same way, there is no difficulty there. In case we have to divide two quantities, again the same issue will be there. If you have to divide two quantities, then there will be minus here, and the same things will occur. Again, the point that I had made, in case of a subtraction, the same issue will be there. The error in the resulting term might swamp the actual value, and so we normally try to avoid a situation like that. And if we do have a situation like that, we make sure that the two ln values are somewhat different, so that the ln z is not too small.